Okay, class, welcome back. And we're going to jump back into integration by substitution and U substitution. Once again, this is a powerful method to be able to solve a much wider variety of integration problems. So we're going to continue on with integration by substitution. And more specifically, we're going to be talking about how we can solve much more complex functions by multiplying and dividing by a constant. Now, this is a great topic to be talking about after spring break because it's going to both allow us to review integration by substitution and add just a little bit something extra on top of it. Okay, so just to sort of refresh our minds here, I'm going to give us a few examples. And I want you guys, as I'm writing these out, to try to figure out what the u is going to be and what the du is going to be. Okay, so the first one, a. Let's figure this one out. So we've got the integral of 2x times x squared plus 1 to the 4th power dx. Okay, so looking at this, just take a second and see if you can figure out what the u is going to be and what the du is going to be. Now, hopefully you've been able to figure it out already just by taking a look at it. Now, of course, our u is going to be a function that's nested, right? That's inside. It's going to be the inner function, our u or our g of x. In this case, this is going to be our u. And if our u then is set equal to, x squared plus 1, if I take the derivative of this, right, so I say, then my du is going to be equal to 2x dx. Remember, the dx gets tacked on the side. And then I can do my u substitution and solve. Okay, now hopefully you guys are familiar with that. And we'll get to similar problems like that. But right now I just want you guys to once again recognize what the pattern is, and we'll get into solving these in just a little bit. Now, problem B, okay, similar thing. Integral of 3x squared. And this time we've got the square root of x cubed plus 1 dx. So similar problem. Remember, I can rewrite this square root as something raised to the 1/2 power. In this case, it would be x cubed plus 1 raised to the 1/2 power. And so what I'm going to do here, once again, give you guys a pause. Hopefully you can figure out what the u is. So the u in this one is, once again, going to be inside the bracket right here. So it's going to be that nested function, the inner function here. So this is going to be my u. And if I want to figure out what my du is, then I can say u is equal to x cubed plus 1. So that means pretty much everything else is going to be my du, or I can calculate my du. Du is going to be equal to the derivative of this thing after I've got my u set. Derivative of this thing is just going to be 3x squared. And then the dx comes along, right? Okay, and so then once again I can see, okay, this is my u raised to the 1/2, my du, that's going to take care of this 3x squared dx, and I'm good to go. I can solve from there. Okay, last one, jumping into some trig stuff. Okay, let me draw a line there. So if I go secant squared of x times the quantity tan x plus 3 dx. Now this is a little bit trickier because we're dealing with some trig stuff. You might not be that familiar with it. It's also a little bit trickier because the nested function isn't as obvious, right? There's nothing raised to a particular power in this case. Maybe you've hopefully figured it out by now, but if you haven't, just in case. Okay, so here we've got, this is going to be our u. It's inside the parentheses here. And then our du is going to be, let's figure that one out. U is going to be equal to the tangent of x plus 3. And the du, remember the derivative of the tangent is the secant squared dot dx in this case. Remember, keep that dx there, it's going to account for it. Then I can once again rewrite this. I can replace this as u, and this become my du. I can rewrite it, use u substitution, take the integral, and then go backwards from there. So plugging the x values back in. Now, I purposely didn't sort of mush these on here so that I could show you guys how I can just alter these. So consider, I'm going to put a little line here. and we're going to be talking about sort of the alternate reality version of these same functions. Okay, and so function a, look at here, I've got the integral of 2x times this function, x squared plus 1 to the 4th power dx. Now, all I need to alter this just a little bit is I'm going to get rid of this 2. So if I go x times x squared plus 1 to the 4th power dx, that's parentheses, and if I try to figure out what my u and my du are going to be, well, my u is going to be the same, right? That's going to be nice. So my u is going to be equal to x squared plus 1. But then my du is going to be the exact same thing, right? That it was over here, just like this. But the problem is, when my du is the same, because I got rid of this 2 right here, all of a sudden there's no 2 here. So what can I do? I've got to do an extra step, an extra half step. And it's going to involve some constants, but there's this extra half step that I need to take in order to be able to fully solve this problem. Now let's do the same thing with this guy. Okay, so I'm just going to alter it a little bit. Instead of 3x squared times a quantity, it's just going to be x squared times a quantity, or the square root of x cubed plus 1 dx. And hopefully you guys are a step ahead of me by now. So my u is going to be the same. It's going to be x cubed plus 1. du is also going to be the same, right? So this is going to be 3x squared dx. But once again, I got rid of this 3 out front, so somehow I need to be able to account for that. Same thing here. Instead of getting rid of a constant in this case, I'm going to add a constant. 2 times the secant squared of x tan x plus 3. So just how I basically took this whole function and removed the 2, or divided this whole function by 2, took this whole function, divided by 3, or removed the 3. This one I'm multiplying it by 2. And so my u is going to be the same as before. U is going to be equal to tan x plus 3. So it doesn't really change my u, and it won't change my du, but it will change how I'm going to have to approach and solve these problems. So secant squared x dx. So in this case, when I do my u substitution, I'm going to end up with a u here, and then these two guys are going to become du, right? Secant squared x dx. But then I've still got this 2 somehow that I need to account for. Okay, so how do I do that? And that's what we're going to be basically talking about today. So this is a pretty simple and straightforward rule that you guys may already be familiar with. But all you're going to end up doing is you're going to manipulate these functions by sort of multiplying them by 1 to make it fit. So you're just going to sort of start mashing constants into the function to make it fit and manipulating them in that manner. So once you have the patterns figured out, that's great, that's awesome, you're most of the way there, but you just need to do a little bit more massaging and mashing of the function to get it to where it needs to be completely solvable. So the theorem that we're looking for, and we've got this written out before when we were looking at the properties of integrals. But basically, if I have a constant in my integral, in my integrand, right? So I'm taking the integral of a constant f of x, I can pull that constant out front. That's all it's saying, is I can, just like with derivatives, I can kind of ignore the derivatives, they go along for the ride. With integrals and integrands, I can basically just pull that constant out. Now let's take a look at the first problem up here, problem A, that I was just doing. All right, so let me go ahead and just box this and put constants. That way you guys can look back in your notes and know exactly what rule this comes from. Now here's the example that I want us to go through. Now be sure you guys are writing this down closely. You're coming to class with any notes, any questions that you have. Okay, so we've got our integral here, x squared plus 1. This is the second version of problem A that I just wrote. So we already know what our u is going to be. Okay, we figured this out already. So our u in this case, u is going to be equal to x squared plus 1. Then my du, I can either pick it out from here, or more importantly, after I have my u, and this is what I urge you guys to do, is once you have your u, is just to take the derivative of this, and this is going to be a good practice that's going to help us very, very shortly in our future lessons. take the derivative of this, and this will give you what your du needs to be. Now if I start looking at this, once again, I'm missing a 2. I'm missing a 2, so I can't do a direct substitution. I can definitely substitute this. So this is just going to become, this whole thing is just going to become u squared, right? But then I've got this x dx that doesn't quite match over here. So what I need to do is to multiply this equation by 1, right? That's going to keep things balanced. It's not going to really mess with the algebra gods. It's not going to anger the algebra gods at all if I just multiply the whole equation by 1. But I'm going to multiply it by a very particular and intentional piece of 1, or I should say style of 1. And so I'm going to multiply it by 1/2, not just 1/2, right? So I've got to multiply it by 1 times 2. So 1/2 times 2, that's just 1, right? Not angering the algebra gods. So that looks good. So then I'm just going to keep the rest of it the same. X squared plus 1 squared dx. Now if I rewrite this, now I'm going to take this 1/2 and I'm going to pull it out front. That's the first thing I'm going to do. 1/2 out front, because I don't really need it, right? What I'm looking to try to do, the purpose that I'm trying, the reason I'm doing this, is to take this 2x, du, man, this is an extra credit opportunity missed right here. I caught it myself though. 2x dx, and I'm trying to basically have that inside my integrand. So I've got x dx, I don't have the 2x dx. So I'm going to pull this 1/2 out front because I know I'm not going to need it. And so then here I'm going to say, I'm going to rearrange things a little bit here. So I'm going to put the x squared plus 1 squared, and then I'm going to take this 2 times x, and I'm going to put it right here. 2x, and then I've still got this dx here. So all I've done is I've just rearranged things, and I've used this constant rule to do exactly that. So multiplied by 1, 1/2 comes out front right there. This 2x comes right there. This goes up front right there. It's still in the integrand, not all the way up front, right? It's got variables in it, so I can't do that. And then I've got my dx right there. So this exactly equal to this exactly equal to that. So just massaging, just manipulating. And all of a sudden, I've got my u and I've got my du, right? So here's my u, and here's my du. Now I can do my substitution. Now I can do my u substitution and solve the problem, okay? So let me rearrange things here real quick. So doing my u substitution, let me rewrite it here before we get going. 1/2 x squared plus 1 squared times 2x dx. And I'm also going to write over here, remember that our u is equal to x squared plus 1. This is something that we just kind of picked. We just kind of made up. I always enjoyed trying to figure out what my u's were going to be because it added a little bit of creative license, and critical thinking is just understanding what the problem is doing. So now I'm just going to replace my u's. So I've got my 1/2 going along for the ride. This whole thing becomes u. Now the whole thing on the inside becomes u. I've kind of been ignoring this squared power, but now it's got to come into play. So this whole time it's been x plus 1 squared, and since u is x plus 1, it's just going to become u squared. Now this 2x dx, that's going to exactly become du. And now I've got an integral that I can solve pretty easily. Thinking of the u's as x's or any particular variable, I can now just say, okay, this is going to be equal to 1/2, and then I've got u to the 2 plus 1 over 2 plus 1 plus c. And then I can rewrite this. I get 1/2, and this is going to be u cubed over 3 plus c. Now the 1/2 does get distributed into the c, remember, but it also kind of gets absorbed, right? So I don't know what c is. It's an indefinite integral, so as long as there's just a c tacked on the end, I'm good. So now I can just rewrite this 1/2. I can pull this 3 out. This just becomes 1 over 6 u cubed plus c. And now I don't have my total answer, but I'm so very close. Now all I need to do is plug in my value of u right here. And so instead of 1 over 6 u cubed, I've got 1 over 6 x squared plus 1 cubed plus c. And this is my 100% correct answer. Now, as always, if I wanted to check, right, real quick, this is a 30-second check that is going to verify that you've got the right answer. I encourage you and implore you to do this with every single one of your problems. So of course we need to do the chain rule here. We've got a function inside of a function. So the 3 is going to come out front. So I've got a 1/6. 3 is going to come out front, taking the derivative of the outer function right here, squared. And we need to multiply by the derivative of the inner function. In this case, x squared plus 1. This is going to be 2x times 2x plus, of course, our c just becomes a big fat 0. So here I've got a 3 times 1/6, 1/2, and then I've got x squared plus 1 squared times 2x. Drop that, or drop the 0. And so I've got this 2x times 1/2. I'm going to just move this around a little bit. So the 2x is going to come out front, multiply by the 1/2, and I just end up with x times x squared plus 1 squared. And that's exactly what I started with. This is exactly the function that I took the original integral of. So now I'm good. So now I dealt with how to manipulate these functions so that I can use constants. And all of a sudden, it just greatly increased the amount of integrations that I can do and the types of problems that I can solve. Okay, so we'll talk about this in class a lot more tomorrow, and we'll continue on with substitution. I'll see you guys then.